Good morning, everyone. Okay, we'll start in just a minute or so. We have 2-3 minutes. Okay, I have 3 people now. If you guys have any questions, we can discuss. Otherwise, I'll start in maybe say 2 minutes. Any questions?
Yes, good morning.
Good morning. Any questions from anyone before we start about whatever we have discussed so far? You can ask from any topic. Any questions as such? Okay. All right, if there are no questions, so if you're interested, you can write to this account mentor. If you prefer writing, write to this mentor. If you prefer directly interacting with me, you can unmute yourself and speak up. Okay, let's start. So today we are going to discuss linear regression. So just to give you a heads up, today's class will be a little mathematical. So in case you get stuck, or if there is something which is not clear, you can ask me any number of times. Okay, don't feel shy. Ask me any number of times. Okay. Now, if it's something that you do not know, in that case, I would recommend that you go back, perhaps read about it, and try to think again what I just said, okay, or what I said during the class. So if you do not know about a certain topic, in that case, I would recommend that, okay, you go back, revisit that topic, because we are going to look at a lot of mathematics today that you have seen in the past, okay? But if you are not from the mathematics background, I believe everybody would have done basic differentiation at some point in time. So if you don't remember all of that, I still request after this session, you go back and revisit some of those basic differentiation rules. All right, let's start with linear regression. So the idea is this: I'm going to start with univariate regression. Okay, the univariate means that there is one feature only. There's a single feature. And if you have one feature and this output as 1, okay, this is also called as simple linear regression. There is a specific name for it. Okay, also called as simple linear regression. Okay, also called as simple linear regression. Okay, so I'm going to start with a generic example. Let's say that so my output is continuous since I'm doing regression, and input feature, it's a real, I mean, it's a continuous feature. Maybe say this is like this. Okay, and the output is, again, you can think of anything. Let's say we are trying to predict let's say height from H. Okay, you're trying to predict height from H. You can take any example that comes to mind. So let's say the heights are, I'm just putting some random numbers, okay? It's not related to the actual units. Maybe say 13.7, 14.6, 15.8. Okay, let's say this is what the numbers are. So let's say you draw this on a scatter plot. You draw this on a scatter plot, or I mean, you can put in generic numbers that would be more appropriate, just to illustrate something. Okay. So I'm just putting in some generic numbers. Let's say A1, A2, A3, and this is some Y1, Y2, Y3. Okay. So let's say if this is the point, which is say A1, and this is say Y1. If this is the point, let's say this is A2, and say if this is Y2, and if this is the point, let's say somewhere here, which is say A3, and the output is, maybe I'll just keep it a little above. Maybe say here, so this is A3, and this is say Y3. Okay. My objective is to fit a line. Okay, my objective is to fit a line. I think we discussed it yesterday. So my objective is to fit a line whose distance with respect to these points is the minimum. Okay, that is what we have to do. See, there are infinite lines possible. I mean, do you guys remember what we discussed in the last class about linear regression? What is the motivation behind it? See, we want to fit a line to this data that we have. Okay. Now, this line, okay, can be anywhere, right? If you think about it. So how do I decide which line to pick? How do I decide which line to pick? Can you comment on that?
Which is closer to all the data sets.
Which is closer to all the data points. So I'm going to show you how to find that line, okay, which is closest to all the points. See, this is important, closest to all the points. This is a very important thing. Okay. All right. So how do you define the equation of a line? What do we say the equation of the line is?
Y is equal to mx plus c.
Y equals to mx plus c, right? I'm going to use the symbol y hat because y is my actual value.
Excuse me, sir. Excuse me. For what purpose we are using y equal to mx plus c? Why do we use here?
We are trying to use this line for making a prediction.
Yeah, I know that line prediction is, I got it. That we are using the formula y equal to mx plus c. You told, right? For what purpose? We have so many form. I just want to clarify that why do we use this formula here? That's it.
Okay, you're saying that why can't I use another formula? That's what the question is.
Yes.
I'll show you how to do that as well. Do you remember the last example that we saw?
Yes, sir.
The experience versus age. So visually, what was the best function that it appeared to you over there? The salary versus experience example. Did you observe in the last class, we saw a data set where the relationship between the inputs and the outputs, they were actually linear.
Yes, they are all close to that line.
Right. So in the hope that the points that I have, they have so you can say the input feature, if it has a linear relationship with the output, okay, I will try to learn a line. Does that make sense?
Yes.
Okay. If it had a relationship which looks like, say, a parabola, then I will try to learn a quadratic function. If it has maybe say a relationship which is kind of cubic, I'll try to learn a cubic function. Okay. Now listen to this question very carefully. Right now I'm trying to show you how to learn the values of m and c for a linear function. Okay. What if, let's say, so if I give you say 3 features, you will be needing 3 axes x1, x2, and x3, and 1 output axis y. So you will need at least a 4-dimensional plot, right? Yes or no?
Yes, yes.
So if you need a 4-dimensional plot, so a linear function in 4 dimensions, it's considered to be a 4-dimensional hyperplane.
Okay.
So think of this. If I give you two features, let's say this is x1, this is x2. You may consider this to be age, you may consider this to be weight. Let's say we are interested in predicting the height.
Okay.
Okay. Now I'm in 3 dimensions right now. What do you think a linear function looks like? So all my points that I'm giving you, they are kind of scattered like this. Okay.
Yes.
My objective is to fit a linear function to this. Do you think it will be a line in 3 dimensions?
No.
So what it would be?
It may be a curve or something.
No, it will not be a curve. I mean, you cannot call it a curve. Curve means it's a curvy linear shape. I mean,
Plane,
if you
right?
call a straight line to be a curve, I mean, it is valid. It's a shape, right?
Yes.
Okay.
Yes.
So in 3 dimensions, we actually call it a plane. Okay. So it may be like this. It may be like this.
Okay.
Okay. So it's a plane. It's a linear function. So currently what I'm trying to show you is how to learn a linear function from a given set of points. Is that part clear?
Yes, sir. Yes, sir.
Okay. I will also show you how to learn quadratic functions, cubic functions. Now, the only objective that I have here is, so before I start describing the objective, if I had one more feature, do you think you can visualize what is going to happen? Can you tell me, can I tell you effectively, like whether to use a linear function or a quadratic function or a cubic function if you cannot visualize the data? Do you think you can, make certain assumptions about it? Think of the question. Let's say you have 3 features. Okay. You will have one output to predict. How many dimensions will you need to plot it?
5.
4.
4.
3 features and 1 output. Okay.
5, yeah, yes. 4.
But is it possible to plot in 4 dimensions?
No.
So if you cannot plot in 4 dimensions, how would you know whether to use a linear function, quadratic, cubic, and so on? So I'm showing you how to use a linear function. Okay. Then I'll show you how to use a quadratic function, cubic function. I will generalize. And then if you want to know what is the best function, what do? We split our data into train and test. We are going to use different functions and we will see on many train test splits. Do you remember the process of k-fold cross validation? So we will use many, you can say different degrees of our polynomial, and we will test it on 10-fold cross validation. On an average, which degree is better? And that is the degree that we will choose to model our data. Does that make sense now?
Yes, sir.
Is it clear now? I mean, more clarity. Okay.
Yeah.
See,
No.
frankly, if I have more than say 2 features, I cannot even visualize. This is a simple example where you can visualize, and that's why I believe you're asking this question. Maybe for these 3 points, a linear curve is not good, right? Yes or no? I believe that's what, that's why the question was raised. For these 3 points, it doesn't look like a line would do well. Maybe a quadratic function would do well, or a cubic function will do well. I believe a cubic function will do well for these 3 points. It will be like this. Yes or no? Does that make sense? Okay, so we'll see how to fit all of these functions in today's class, hopefully in today's class. Okay. All right. So I'm going to use the equation of the line, which is say mx plus c. Okay. So first of all, we need to understand why this is called as linear. Okay. Can you tell me the generic quadratic equation? So how do you write a quadratic equation? A generic quadratic equation.
Ax square plus bx plus c.
Correct. Okay, that's how we write it. Ax square plus bx plus c. Why it is called as quadratic? Because the highest power of the variable, is
2.
2. Listen to this very carefully. The highest power is 2. Okay, the highest power is 2. Okay, keep this in mind. That's why it's called as quadratic. See, you can see that there is a component of power 1 and there is a component of power 0 as well. Does that make sense? X to the power 0 will be 1, right? So C is the coefficient for x to the power 0, B is the coefficient for x to the power 1, and A is the coefficient for x to the power 2. Okay. Now, how will a linear equation look like?
AX plus B.
Ax plus B. Essentially, if you think about it, this is mx plus c, where A is m and B is c. Okay. So here x is having the highest power as 1. Okay. And B is having the power of x to be the 0. Anything to the power 0 is a 1. So you can simply write it as it is. Okay. So this, as you can see, is the highest power is 1. Keep these things in mind because this will help you understand what is about to come next. Okay. Now look at the equation that I'm using. Okay. Look at the equation that I'm using. What is the power of x1?
1.
1. Okay. So can I say this is linear?
Yes.
Okay. So power of x1 is 1. Okay. That's why the name, it is linear regression. Okay. So that's the first thing. Okay. Now there is a catch, and the catch is this. If you look at this quadratic equation or any linear equation, what are the known things to me? Okay, look at this quadratic equation. If somebody gives me this quadratic equation, let's say equal to 0, what will be the known things to me? Will it be A, B, C, or will it be X? What do I determine from a quadratic equation?
X will be
Okay, I'll repeat this in more detail. Okay, if I give you a quadratic equation, okay, what do you typically find from a quadratic equation?
Roots, right?
The roots. Okay,
Yeah.
you find out the roots. And what are the roots? What are the roots?
X.
The values of x. Okay, so how many values do you get if you have a quadratic equation?
2
Two
roots.
values. Okay, 2 roots. So the degree of the function tells you how many roots are there. Keep this in mind.
Yeah.
This will also be important. Okay, so what do I know in this equation? I know A, B, and C. I do not know X. That is the purpose. I mean, that is the objective for me to find. Okay, keep this in mind. Now, in this equation, what is it that I do not know in mx1 plus c? Think about this carefully. What is it? M and C are the unknowns. Okay, M and C are the unknowns. So it is equivalent to saying I do not know A, B, and C. Okay.
Yeah.
Yes.
So those two things do not try to correlate. Okay. So I'm just trying to let you know, okay, here we are interested in finding the values of M and C because I know the values of x1s from my data. What are the values of x1s from my data? If you look at this plot,
A1, B1.
A1, A3, and A2.
Yeah.
A1, A3. So these are the different values of x1 that are available to me. Okay. And my purpose is to find that M and C which minimizes the distance. So see, if I tell you what M and C is, you will get a line, right? Yes or no?
Yes.
Yes.
Okay. I mean, depending on M and C, the orientation of the line will change. Okay.
Yeah.
So for different values of M and C, I will get, you can say different lines. Let's say if this is another line, I can find the distance of the points with respect to this line also. Yes or no? So this is the
Yes.
distance of this point. This is the distance of this point. This is the distance of this point. Okay. If I sum this distance up, let's say D1, D2, and D3, and let's say I do it for the, let's say red line as well, which distances do you think will be minimum?
Red line.
Red line, right? So my objective is to find that particular line. If you think red line is the optimal one, I will say that my objective is to find this red line, which has the least sum of the distances with respect to that line given to you. So my objective is to find M and C for that line. Okay. See, there can be infinite lines. Okay. So I'm just assuming my current line is this mx1 plus c with a certain value of M and C. Okay. All right. Now let's see what a M and C are. Okay. This is called as C, where you hit. So where you hit the y-axis. Okay. I should have drawn it a little, okay, because it will coincide with y1. Okay, let me just put like this. So this point where it hits the y-axis, it's called as C. Where you are hitting the y-axis, this is called as C. So if you think about it, like for any given line, C can be positive or negative, or it can be 0. When it will be 0?
Passing through the origin.
Passing through the origin. Okay, so if I say my line is passing through the origin, which term is 0?
C.
C is 0. Okay. All right. Okay. So you will just have m into x1. All right. M is also called as the coefficient. Okay. M is also called as the coefficient. The combination of the things that you are trying to learn, in this case M and C, they are also called as parameters. Okay, they are also called as parameters. These are the things that we are trying to learn. Okay, these are the entities that we are trying to learn. Okay. All right. So let's see how we, define the distance between the points. Okay. So if you look at this red line, before that, let's discuss about M. What is M? So see, if I extend this, okay, if I extend this, do you see that this line makes an angle with this x-axis? Let's call this angle as theta. Okay.
Yes.
M is nothing but the slope tan of theta. Okay, M is nothing but the slope, which is tan of theta. You can actually make it here also. Okay, you can actually make it here also. So this would be the theta again. Okay, if this line is parallel to this x1 axis. Okay, do you know what property ensures that the thetas are the same?
Corresponding angles.
Corresponding angles. Okay, so if you compute the same theta for the line that I've shown, this one. Okay, you'll still get the same tan theta. And in trigonometry, how do we compute tan theta?
Opposite side by hypotenuse.
No. So if this is the perpendicular, and if this is the base, if this is the base, tan theta is given to be perpendicular by base. Does that make sense?
Yeah.
Okay. So this is what tan theta is. All right. So M is nothing but the coefficient, which is giving you, you can say, the power to your feature x1. So M kind of tells you what is the importance of the feature x1. Okay. And C is like a constant which is added to every prediction. Okay. All right. Let's see how to find this M and C. Okay. So I'm going to write, a very simple equation. Let's try to see it. Let's say these are the 3 points. Okay. And this is one line with respect to which I'm going to compute the distance. This line is M times x1 plus C. Okay, this is your M. Sorry, this is your x1 and this is your y. Okay. All right, let's try to find out the distance for this point. Okay. So if this is say A1 and if say this is y1, okay, what do you think will be the prediction from the line? What do you think the prediction from the line would be? How do you get the prediction from the line for this value A1?
Draw a perpendicular from E1 and wherever it hits.
Wherever it strikes, this would be the prediction, right?
Yes.
Okay. What would be that value?
Will be somewhere less than y1.
No, that is true, but how do you compute it? You have to substitute A1 in this.
Yeah.
Okay.
As simple as that. And that would be the value that you see on the line. Okay. So we have M times A1 plus C to be the prediction, right? Yes or no?
Yes.
Okay. So the actual value is given to be y1, and this is the prediction, let's say. Okay. This is your actual, this is your prediction. Okay. Let's say this is the input x1. Okay. All right. So this is your A1, and this is the prediction that you get. For let's say the next value, let's say this is A2. Let's say this number is okay. So what would be the distance? Can I say the distance would be? So this value is going to be M times A1 plus C. So this is the distance I'm measuring. Yes or no? Is this the distance I'm measuring?
Yes.
Okay. This distance is called as, let's say, D1. Okay. This distance is called as D1. All right. Let's do it for the second point. Okay. So if you do it for the second point, you are going to measure basically, the distance between. So if you do it for the second point, this is where you can say the prediction is. Okay. So what would be this value? M times A2 plus C. Does that make sense? And the actual value, let's say, if this is given to you, this value is say y2. Okay, so this is y2. Okay. So what would be the difference between the values? What would the difference between the values? Basically, can I say y2 minus of this? Does that make sense? I can put it like this, right? Okay. All right. And A3 is, say, you can do it for the third point also. So let's say this value, if it is there, if this is A3, you're kind of measuring, see, it will become very clumsy. So you're kind of measuring, let's say this much distance. You're kind of measuring this much distance. Okay. So this is Y3, this is M times A3 plus C. Okay. All right. So I want to know how much total mistake I am doing. So what would you do? I want to, okay, what is the distance? How do you define the distance?
D1 plus D2 plus D3.
Okay, so I'm going to measure the distances D1 plus D2 plus D3, right? How do you define the distance at D1?
Absolute of Y1 minus MA1 plus C.
Okay, great. Why did you take the absolute? You answered one of my questions.
Distances are positive.
Distances are positive. A distance cannot be negative. If the distances were negative, what would happen? Can you think what could be the problem?
If I am having one positive and one negative distance and adding them up, it will
That can cancel it
lower the
out.
distance.
It can lower the distance, right? Okay, think about this. If I give you 2 points, okay, there is this one line. Okay, this is one line and this is another line. Okay, which is actually the perpendicular bisector of it. Which line do you think is better? Black or red?
These cross are my data points.
The crosses are your data points.
Then the black one.
Black one is better, right? You cannot use a red line, because if you're using the red line and the notion is that distances can be negative. See, you for this point, I mean, if you think about for this point, okay, let's say if this point is having the prediction maybe say somewhere here. Okay, so this much would be say the negative distance, and let's say this much would be the positive distance.
Nullify each other.
And they will nullify each other. So even in this case, if you go by your interpretation, this red line is also optimal, right? But is it really optimal? No, right? Yes or no? And what about the black line? Don't you think the actual value and the predicted value, they are exactly the same? Because the line is passing through the points.
Yes.
So in that case, the distance is 0.
0.
So your distances always need to be positive. You cannot say distances are negative. That's a property of a distance, okay? You cannot say that you are making a negative mistake or a positive mistake. You always say that you're making a mistake and you are adding up those mistakes. So that's why your distances have to be positive, okay? Your distances need to be positive. All right, keep that in mind. Okay, this is one way to measure it. Can you think of another way to measure it? The distances still remain to be positive.
Squaring.
Square it. Okay. So this is another way to measure it. Okay, I hope you guys get the point. Now, why am I saying that we will prefer, by the way, this? I will talk about this in detail. That's where now the maths start. Okay, we haven't touched any math so far. Okay, let's see this. What would be the total distance? Okay, I'm going to write it very simply. You tell me if this is accurate or not. So if I have n points, okay, if I have n points, what I'm doing is I'm taking the absolute of yi, okay, and subtracting it from, let's call it yi hat. Okay, and what is yi hat? This is m times feature value is x1, I plus c. Does this make sense? See, we are subtracting actual and predicted, right? So this is the actual value for the ith point, and this is the predicted value for the ith point. Aren't we subtracting the two?
I is in the power or I is in
No,
the
I is not in the power. I is just to indicate the index number.
Okay.
Because x1 is my feature, right? Okay, I'm writing it as x1, not as x. Okay. All right. So I is not the power, I is the index. Okay, this is the index of the sample. Index of the sample. All right. Does that make sense?
Yes.
Okay. So x1I will give you the first feature value. The first feature value, or rather, let me call it like this: x1 of 1
Then I say
will
y.
give you the first feature value. X1 of 2 will give you the second feature value. Okay, x1 of 3 will be the third feature value, and so on. Is that part clear? In my case, what is x1 of 1? A1. I took it as A1, right? This was A2. This was A3. So you can think of it like this: given a data set like this, I'm writing it like this. This is x1 of 1. This is y1. This is x1 of 2. This is y2. This is x1 of 3. This is y3. Is this clear?
Yes.
Okay. And you can go on if you have more points. Okay. You can go on if you have more points. Okay. All right. So this is what I have to compute. So my purpose is to minimize it or maximize it to find the best line.
Minimize.
Minimize it. So this total distance needs to be minimized to find the best line. And what are the variables in this equation?
Y.
Again, think. Which y?
X is the
Okay. No. What are the variables in this equation? What are the unknowns that I want to determine?
M and C.
M and C. So I'll be determining this equation with respect to M and C. I'll be minimizing this equation with respect to M and C. So far, so good. Any questions up to this point? Is this clear?
Yes, sir.
Okay. All right. Let's go back to your basic maths. I'm going to show you a function and let's try to minimize it. Okay. Let's say this is some function which I'm making. Maybe say 3x squared plus 6. Okay. This is, let's say, the function that I have, and I want to minimize it. Okay. With respect to this x. Okay. The variable is x. So how do we do this?
dy by dx.
Okay. So let's say if this function is fx, I'm going to call this function as fx.
Yeah.
So what I'll do is I'll take the differential of this function. So what will be the differential?
6x
6x.
plus 6.
6x? No, for a
Sorry.
constant, it is a 0.
Yeah.
Okay.
Just 6.
I hope you guys revised differentiation. What is the differentiation for a constant?
0.
0.
0, 0.
And how do we differentiate any power? Let's say we are doing this, ax to the power m with respect to x. So a is a constant, it comes out. X will be to the power of m minus 1.
1.
And you will multiply this with the dx by dx again. Does that make sense? And this m, the power m also comes out. Yeah, the power m also comes out. Does this make sense? Yes, people. Correct me if I'm wrong. That's how you do it, right? The power comes out of x, and then you reduce the power of x, which is by 1. And then you write dx by dx again. Since dx by dx is 1, you can write this as m into a into x to the power m minus 1. Is this part clear?
Yes.
Okay, so far so good. Okay, so what would be the differential? It would be 6x.
6x.
Okay, all right. Okay. All right. So I have this 6x. What do I do with this differential? This is actually called as the differential, the regular differential. This is also called as the gradient, by the way.
Slope. Right?
Slope also. Okay. By the way, okay, I'll talk about this in detail about slope and all these things. Okay, it will come in an algorithm very soon. Okay, so if I have this differential, what do I do with it to find out at what value this x is giving me the minimum value of fx? I take the differential and equate it to 0. So if I equate it to 0, what do you get? You equate this to 0, what do you get? You get x as equal to 0. you can say this is the root of your equation. Okay, you can say this is the root of your differential. Okay, so what is the power of x in my differential?
Quadratic.
Power of x in my differential. I'm looking at the
No.
differential right now, which is equal to 0. 1, right? So
One.
how many roots will I get? 1.
One.
So if my original equation was cubic, how many roots will you get?
Two
Two.
roots.
2 roots, right? Keep that in mind. Okay. So it depends on what the original equation is that you're trying to minimize. Okay. So you're getting 1 root if the original equation is quadratic. Okay. All right. Okay. So how do I know the value that I have at x is equal to 0 if it is giving me the minima or the maxima? If it is giving me the minima or the maxima. Because a root is not supposed to guarantee the minima or the maxima. There is a check for it. Anybody remembers? No? What you do is you take the double differential. So what would be the double differential?
6.
6. So if your double differential is greater than 0, add the root. Okay, you'll have the minima. See, currently what you're getting 6, right? 6 is greater than 0. So at x is equal to 0, you will get the minima of fx. Okay, you'll have the minima of fx. Let me write it as minimum instead of saying the minima. Okay, you'll get the minimum of fx. Okay, assume that if this equation was cubic, how many roots will I get?
2 roots.
2 roots. So if I double differentiate it, what equation would I have? Linear or quadratic?
Linear.
So if you have a linear equation and you have 2 roots, what you will do? You will put those roots in that double derivative equation. So one of them, if you put, okay, if it leads to a value greater than 0, that will be a minima. And if you have the value less than 0, that will be a maxima. Okay. Does that make sense?
Yes.
Okay. At equal to 0, you cannot say. At equal to 0, that is called as a saddle point. So we are not going to discuss that. We don't need it, by the way. Okay. At 0, we cannot say. All right. But this is important. Yes.
Because it's a quadratic equation, we are using
They're
the
directly getting a constant there.
double differential. But if it is a cubic equation, we
You will get some linear equation as a double derivative, right? So you will put the values of x in that linear equation and you will get 2 values, right? So you will check for which value of x you get a value of double differential to be greater than 0, and for which value of x you get a value which is less than 0. Okay, think about this. Let's say this is my function. Okay, this is my function. This is your x-axis. Let's say this function is maybe say 3x cubed plus 4x squared plus 5x plus 1. Okay, let's say this is the function. This is how a cubic function would look like. Okay, so if you take the derivative of it, what will happen? You'll get 2 roots. What do you think the 2 roots will be? These will be the 2 roots. Okay, so whatever this value of this x is, let's call this as a1. So if you put a1 in the double differential, what do you think the value of double differential here would be? Let's say the function terminates here. Okay, what do you think the double differential value of at a1 would be?
maximum value.
No, not maximum. What would that value be? Greater than 0 or less than 0?
Greater than 0.
Less than 0.
How?
See, this point a1 is giving you what? A maxima or a minima?
It's giving me a maximum.
So if it is a maximum, what would be the double differential value at this a1?
Less than 0. Okay.
Less than 0. Okay. So if this value gives me a minimum, let's say this is a2. So corresponding to a2, what do you will get? Maximum or minimum? Minimum, right? And minimum indicates what?
Greater
The value of double differential would be greater than 0. Is this clear now?
Yes.
Okay. All right. Okay. Now we don't have to go beyond quadratic equations. Okay. You will see that soon. All right. So I hope you have understood this concept. a few other concepts that you need to understand. Let's say I put a constant in front of this function 3x squared plus 6. And the constant is positive. It's a positive constant. Do you think the root changes? Do you think the root changes? See, please note that my objective is to find that value of x at which this fx is minimized. This is your fx now. Do you think the root changes? How do you compute the root? Revise. Derivative of fx divide by x and you equate it to 0. So if you do the derivative, 1 by c is going to come out, right? And this will still be 6x and you will equate it to 0. 1 by c will go to the other side and x is still 0. Did the root change?
No.
So the function definitely has a lower minimum. What is the minimum now? What is the minimum of fx now? At x is equal to 0. 6 by c. Substitute x as 0 in this equation and the minimum is 6 by c. What is the minimum in this case?
6.
6. So the minima changes, but the root doesn't change. Keep that in mind. Okay. The minimum changes, but the root doesn't change. Okay. All right. Keep this in mind. So if you have a positive constant, it will not change. What if it's a negative constant? What will happen? Okay. Think about it. It's a take-home exercise. Okay. Think about it. It's a take-home exercise. Okay. All right. Okay. What we have is this so far. Now you might get stuck if it's a negative thing. Okay. Anyways. All right. So this is what we have about your, functions, and we are trying to find the minimum of a function with respect to the variable. What if I have two variables? What do we do? Let's say the function is like this. Now I have two variables. What do we do now? I asked you to read one more thing with respect to, in addition to regular differentiation. What did I mention? Partial. So you will do partial differentiation now. So this is your function. Now you have two variables, x1 and x2. So you'll be partially differentiating. So this is the symbol for partial differentiation. Okay. This Greek delta that you're seeing. Okay. This is the symbol for partial differentiation. In some books, people write this symbol also, delta, for differentiation. Okay. This is the symbol for differentiation also. And with respect to the variable, let's say you're doing it with respect to x1. So that's how they will write it. Okay. All right. Okay. So I'm going to differentiate it with respect to x1. So if you're doing this with respect to x1, what will be x2 treated as?
Constant.
Constant. So if I differentiate this equation with respect to x1, what do I get? 6x1.
6x.
And you will equate it to 0. So you get x1 as 0. And then you differentiate this equation with the second, with respect to the second variable, you get 8x2, and this is 0, so x2 is 0. Okay. My next question is, if I put a constant outside.
Sanatan, how you're considering that as a 0, like 8x2 is equal to 0? You're
see, how do we find the root? We equate the differential to 0, right? Look at the last step that I did. How did I find that the root of this equation 3x squared plus 6 was 0? I equated the differential to 0, right? You didn't go through what I asked. Anyways. So when we want to find the root, what we do is we get the differential and then we equate it to 0. That will give me the value of the root. Okay. So here also I'm doing the same thing. Okay. So my 0, 0 is the root that I have. Okay. My 0, 0 is the root that I have.
Okay.
So-
Okay. Now
So
I
if
got it.
you substitute x1 as 0 and x2 as 0, what is it that I get? 6. Make
Yeah.
sense? Okay.
Yes. Yes.
Now, if I put a 1 by c outside, where c is the positive constant, do you think the root changes?
Root never change.
Root doesn't change.
Yeah.
Okay, if it's a positive constant.
Yeah.
Okay. All right. Okay. Okay. Oh, all right. Now, just basic things. Are all functions differentiable?
Yes.
No.
If it is continuous. If it is
No.
continuous.
Even if it is continuous, they are not differentiable. Continuity is a necessary condition, not a sufficient condition. Okay. So not all functions are differentiable. Okay. So what are the conditions for differentiability? One is continuity, as you mentioned, but that's not a necessary condition.
Limit of
Limits. Spot on. Okay. So there needs, you need to satisfy two conditions. One is continuity. The function has to be continuous. Second is the function needs to satisfy the limits. The left limit of the function is equal to the right limit is equal to the limit at that value. Okay. Limit at that value. Okay. I'll tell you in simple words, what do they imply? You don't have to really read about all these things. So if I give you a function, let's say this is x, I'm going to draw a function f(x). Okay. Continuity implies that you can make a function without lifting your pen or pencil, whatever you are using. Okay. So tell me about this. Is it a continuous function? Did I lift my pen while drawing it? No, right? It's a continuous function. As simple as that, this is continuity. There is no break. Okay. All right. What about this function? Let's say this is x. Is this continuous?
Yes.
No.
Yes.
Yes.
Is there any break? It is continuous, right? Do you see any break?
No.
It's continuous. It's a continuous function. Okay. What does this function resemble, by the way, if this is 0 and this is symmetric? What is this function, by the way?
Absolute value of x.
Absolute value of x. Okay. This is your function fx. Okay. All right. So fx is this given function is continuous, but this is not the only condition. Okay. You need to satisfy one more. Let me show you a function which is not continuous. Let's say I take an example. Let's say this is x. So my function is like this. Imagine that. Okay. I'll define this function. So let's say fx, if this value is 0. Okay. So fx is say 2 if x is less than 0 and fx is say 3 if x is greater than 0. Do you think this function is continuous?
No.
There is a break, right? At this point, can you see that? Okay, there is a break at this point. There is a hidden jump kind of a thing, okay, which is happening here. So this is not a continuous function, okay? All right, so this is the function that I just made. All right, so I hope continuity is understood. Let's talk about the second point, which is satisfaction of the limits. So one simple way to interpret it is this: when you are making a function, okay, the function should not have sudden, you can say turns, sudden sharp turns. The function should not be steep at any point. Okay, think about this. Is this function, the absolute x function, is there any sharp turn at any point?
Yes.
Are you making any sharp turn? Is the transition smooth at every point?
No.
No, right? At this point, you make a sharp turn. What is this value?
Yeah.
At x is equal to 0, you make a sharp turn. So at this point, the function is not differentiable. Okay, at this point, wherever, okay, the transition is not happening, okay, the function is not differentiable. The left limit and right limits and the actual limits, they'll be different, okay. One of them would be different for sure, okay. Now, if I would have asked you in this range of say 3 to 5, is this function differentiable? Is this function smooth?
Yes.
Okay. So this is a smooth function, right? There is no transitions if you think about it. And in the range of 3 to 5, is it continuous?
Yes.
Okay. So in the range of 3 to 5, it is, continuous as well as smooth. So it is differentiable. But if I talk about in the range of say minus infinity to infinity, is the function differentiable?
No.
No. So it is not differentiable in the entire domain. Keep that in mind. So absolute functions are not differentiable. Okay. For a function to be differentiable, it has to satisfy at all the points within that range, within that minus infinity to infinity. So if you are given a range of a to b, the function has to satisfy both the properties. So function needs to satisfy both the properties. Okay. For you to call it differentiable. Okay. For differentiability, the function needs to satisfy for all the points between a and b, for all, let's say x between a and b. All right. That's how mathematicians write it. This is the symbol for all. Okay. This means for all x. Okay. For all x in the range of a to b, if a is minus infinity, b is infinity. So if the function is continuous for all values of x, and it is, you can say, having a smooth transition, okay, then the function is differentiable, otherwise not. Okay. Is this point clear to everyone? Yes, people. Is this point clear? So is absolute x differentiable? No. In the range of minus infinity to infinity, it is not. Okay. It's not differentiable in that range. Keep this in mind. Okay. Okay, what is an alternative function which is similar to absolute x, but it is differentiable? So can we make at x is equal to 0 the transition to be smooth?
X square.
X squared. Parabola. Okay. All right. So x square is smooth. There is no sharp turns. Okay. It is differentiable everywhere in the domain of minus infinity to infinity. So I'll put it like this. Any function, okay, let's say you are doing this, you're writing any function of any variable x and you are squaring it up. Okay, you are squaring it up. If this function is linear, the square version of s is always going to be differentiable. If you write any function and you square it up, as long as this function is purely linear, okay, the square of this would always be differentiable. It will be continuous and it will be the limits in that range of minus infinity to infinity will always exist, will always be the same for every point. Okay, so keep this in mind. This is a good rule to remember. As long as the function is linear and if you square it up, okay, any function which is linear and if you square it up, that function is always going to be differentiable because it will be smooth. So any squared function is differentiable as long as the inner thing is linear. Okay, so if I make a function like this, say x plus 6 whole square, what can you say about the inner part? Is it linear? Is x plus 6 linear?
Yes.
Okay, what can you say about 5x plus 6? Is it linear?
Yes.
Okay, so you can always claim that the square is a continuous function. Okay, what can I say about this? 5x plus 6 minus 3.
Is also linear.
Also linear, right? Okay. One more thing you have to remember is sum of differentiable functions. Okay. Sum of differentiable functions. Okay, it's also linear. Okay, I mean, if you have multiple differentiable functions, if you sum it up, okay, if you sum it up, that will also be a differentiable. Okay, if individual functions are differentiable and you have a sum of them, so the entire function is differentiable. Okay, because every element is differentiable. All right.
Yeah.
One more thing. Now we need to understand one more concept, which is called as convexity. This is perhaps the most important aspect in ML, I would say, from the perspective of theory. That's my opinion. Okay. Now, I want you to tell me, let's say if I give you this function, is this function differentiable?
Yes.
It is, right? Okay. Let's think of this function. Is this function differentiable? Let's say this is x squared. Is this function differentiable?
Yes.
What can you say about, I mean, let's say the difference between these two functions? How would you, so both are differentiable, okay, but what is the fundamental difference between the two functions?
The down function is both sides going upward,
Mhm.
and this one both left.
Good point, good point. So, okay, how many roots can I expect in this range? How many roots can I expect in this range? What can you comment about this?
No roots.
No, there will be roots. Roots are nothing but the transitions, where the transitions are peaking or they are actually going the least. How many roots will be there in this range?
4 roots.
Let's say this is A and this is B. So this is one where you achieve the maximum. This is the minimum. This is the maximum and this is the minimum. So there are 4 roots. Okay. So it must be a power 5 equation.
Excuse me, sir. But the roots are, and the graph is cutting the x-axis, then only we can say the root, right?
No. That's not the point. No. Where it achieves the minimum or the maximum, that is the root. It is not necessary where it hits the x-axis. If it hits the x-axis, you are saying that the function value takes a value as 0. Okay.
Yeah.
It's not necessary the function will be always equal to 0, right? Any function will be equal to 0. If it passes through the x-axis, you mean that, okay, the function value is 0, okay, at that point. So I'm not talking about that. Wherever there is a transition happening, okay, a peak, or you can say, I mean, you must have heard of this term crests and troughs. So wherever there is the maximum of a crest or a least part of a trough, okay, those are the roots. Okay.
Okay.
How many roots are there in this parabola?
1, right?
1. Okay. So all those functions, okay, which have a single root, okay, they have a global minimum. Okay, they have a global minimum. They are called as convex functions. Okay, they are called as convex functions. Keep that in mind. So which of these two functions is convex?
The lower one.
Lower one. So squared functions are typically convex. Keep that in mind. Okay, squared functions are convex. Okay, I want to ask you this. Is absolute also convex?
Yes.
Is that this is also convex, right? There is, I mean, you can draw this absolute even above. Okay, is this convex? Yes, right? Global minimum only.
So basically, when there is only one root for a function, it is called.
And if it is the minimum, and if it is the minimum, see, I can make a function like this, right? What can you say about this? Is it the minimum?
No.
No, right?
Yeah.
So in this case, you can call it concave if you want to call it. Okay, this is concave. All right, this is the reverse of convex. We will only talk about convex though. Okay, but this is called as convex. This is called as convex. Concave, the below part. Okay. All right. Okay. Now, a function which has many roots. Okay. So if you look at how many minimum roots are there in the above function?
2.
2.
2, right? Let's say this is x2 and x4. So out of these, if I ask you what is the global minimum, what would you say? Out of x2 and x4, which is the least one by looking at it?
2.
X2 is the least one, right? So at x2, whatever the value that you get, let's say this is x2, whatever this value is, you substitute x2 in this function, whatever the value that you get, okay, that would be, I shouldn't say x2, okay, I should write it like this. This is say f of x2, okay, and this is f of x4, okay. You substitute the value of x4 in the equation and you will get a higher value than f of x2. So f of x2 is the lower value. So can I say f of x2 is the global minimum? Yes or no?
Yeah.
It is the least amongst all the minimums, right? Okay. A convex function is one which has only one global minimum. Keep that in mind. Okay. So there are functions which will possess a global minimum. Okay. However, the number of minimums will still be many. Okay. in this case, okay, the squared function is convex, and the key part is only 1. Okay, the number of roots, the minimum value will be 1. Okay, minimum value will be 1. Okay, let me ask you this one more time. Think about this. Let's say this is how the function is. What can you say about this function? Is this convex?
No.
Yes. There are many roots, right? There are infinite roots in this range.
Yes.
But what is the minimum value of all these roots? The same, right?
Same.
It is parallel, let's say, to the x-axis. So what is the minimum value? It is 0, right?
Yeah.
Okay, so this is also convex. Okay, now my second question is, are all convex functions differentiable?
No.
Probably not. Yeah.
No. No. Okay. No, not probably not. I mean, think of absolute x. Absolute x, I said it's convex, right? We just proved, I mean, discussed a few minutes back that absolute x is not differentiable. Okay. So not all convex functions are differentiable. Okay.
Okay.
So the method that you have seen so far, that you minimize the equation, okay, you minimize the equation for finding the root of the function. We use differentiability, right? That is what you guys know. So if I give you this function and you're trying to minimize this function, the only way that you know so far is to differentiate it, right? Somehow, if I magically make this function as convex, what will be the benefit of it? What will be the benefit of it? It will have one root only. Okay. So if it has one root, okay, and if it is differentiable, okay, it will be a unique root. Yes or no? Think of this. See, how many roots will you think are there? There might be infinite roots, right? At all these values, don't you think the function value is the same? Yes or no?
Yes.
Okay. However, if you think of any function like this, okay, but this function is not differentiable. It doesn't satisfy this. But if you think of squared functions, you will get only one root. Okay. This function is also not differentiable because it takes a sharp turn here and here. It takes a sharp turn here and here. Okay. So keep that in mind. Squared functions are something that we will prefer all the time. You will see, if you want to read research also in machine learning, you will see squared functions mostly. Okay.
So squared functions are mostly differentiable, but when there is a sharp curves, we can't differentiate that function, right?
Yes. So in squared functions, you will not see sharp turns anywhere because they are differentiable. Okay.
Okay.
Okay. All right. So keep this in mind.
Yeah.
The squared functions which I mentioned, they should be of this type.
Okay.
You're doing the power 2, which is the squared function. The inside should be linear. There should not be any exponent. There should not be any sine. There should not be any cos theta, and not anything like that. The function has to be simply linear.
So it has to be f of x, not f of like f of x1 or f of x2 like that.
No,
like
it can be a composition of multiple variables also.
Okay.
This can be a composition of multiple variables also. Okay. All right.
Okay.
Can be a composition of multiple variables also. But there should not be any trigonometric function inside this, logarithm inside it.
Okay. Fine.
That will not guarantee it.
Like that. Okay.
Okay. But if it is linear, then I can guarantee that, okay, that is going to be convex. Okay.
Okay.
So such type of functions are also convex.
Yeah. Can you please go to that diagram, like this
Which
one? This one. So you said like we have a root in this, right? Like we have a multiple roots, but it was taking up sharp cuts, right?
Correct. So this is not differentiable, right?
Okay. So, and this is not a square function also.
This is not a square function also.
Okay.
I'm just saying that we would prefer those functions which are square by nature, and they will have they will be convex, so they will have just one root.
Okay.
They'll have just one root.
Sure.
Okay. All right. Okay. Keep these things in mind. And see, by the way, there are other ways to solve for the minimum when the function is non-differentiable, but it is convex. But that is beyond the discussion right now. Okay. I'll not discuss it at all. If you're interested, I will tell you what to read. So there is a whole chapter on how to solve for non-convex functions. That is called as non-convex optimization. Then I will have to actually take up another course for you guys that course will be called as optimization theory. So to understand the basics of machine learning, let's only focus on convex functions. Okay, is this clear? But you can find out the minima for even a non-convex function and even a convex function which is not differentiable. Okay, see, what is our objective? Our objective is to find the minimum, right, for the function that we came up with. We wrote this. See, why am I telling you all this stuff? Because ultimately I want to minimize this equation that I wrote, this one. Okay, I want to minimize this equation. So for me to describe how to minimize it, you need to know all these things. Okay, is this part clear? Okay, but there is a theory behind, there is mathematics for how to minimize non-convex functions. There is a theory for how to minimize convex functions that are not differentiable. Okay, and there is a theory for the functions which have many roots, how to find the global minimum for it. There are work in those directions as well, but that is beyond the discussion. Okay, so far, I mean, in your entire curriculum, the algorithms that you will see, okay, they are all convex. In your curriculum that are there. In your curriculum, I'm saying. All right. So we have discussed like how to optimize it and find the roots. Okay. Now, differentiation is one way to do it, as long as the function is differentiable. So this is the function that I have, right? This was the function. I was taking the absolute of it. Is this function differentiable? Is this function differentiable? We just discussed so much about absolutes.
No.
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 So can you change something to this, something in this function, so that the inner component is fx, which is linear, and you just do something in the powers, so the function is still positive?
Square.
You can square it.
Square it up. Okay. So we'll be using this. That's why I said that is preferred. Okay. By the way, if you are interested, okay, let me tell you this function is convex, by the way, but not differentiable. If you are interested, like how to solve this, you can read about linear programming. If you are interested to read about this, okay. And if you want to know about how it is done in Python, so nobody has done it explicitly, but you can use a library called as Groovy to do it. Okay, so Groovy is the Python library which can help you do linear programming. Okay, Python package which can help you implement this. But you have to read first about how to do linear programming. Okay. Okay, this is something which is a suggestion. I don't recommend reading it if you are not comfortable with maths. Okay, so we will be minimizing this. I'll share all these notes, don't worry. Okay. Okay, so let's see how to minimize it. So I want to give it some name. Okay, can I call this function as, say, sum of absolute errors? Yes or no? Does that make sense? I'm minimizing the sum of, I mean, taking individual errors, individual mistake, and I'm summing the absolute of it. Does that make sense? Okay. If I put a 1 by n in front of SAE, can I call it as mean absolute error? These are the things that we have seen in k-nearest neighbors also. They were evaluation metrics.
Yes.
Okay. What would you call this then? This function. Sum of? What are we doing with each error? We are
Where Euclidean.
sum of squared errors. Euclidean has a root. Is there a root here? No, right? So this is sum of squared errors. If you put a constant 1 by n outside of sum of squared errors, what can I call it? Mean squared error. Okay, make sense? All right, let's see this. There is one more popular function. Some people write it like this. So 1/2 of sum of squared errors. If you see, or some people will also use this 1/2 n of sum of squared errors. Okay, they will call this function as ordinary least squares. N is the number of samples. Okay, number of samples. This is also called as ordinary least squares. All right. Okay, now I have a question. Do you think that if I minimize any of these terms, I'm not talking about these two. Okay? If I minimize any of these two terms, like sum of squared errors, mean squared error, ordinary least square errors, do you think if I minimize them, do you think MNC will change? Do you think MNC will change? The roots will change. Look at the constants outside. That should tell you something. Are the constants positive? Are the constants positive? Okay,
cannot
think
say
of this first constant. What is the first constant in sum of squared errors? 1. What is the value of C? 1. I can write it as 1 by 1, right? What is the value of C in this case? In mean squared error? N. N is a positive number, right? Here, C is 2. Here, C is 2n. So do you think MNC changes if I use any of these functions? We just discussed this a few minutes back. It doesn't change.
Yes.
Okay, it doesn't change. I showed you the roots that you will get. MNC will stay the same. The minima will change. The roots will not. See, what is my purpose? Is my purpose to determine MNC, or is my purpose to determine the minimum value of this function? What is more important to me?
minimum value.
No, my more important is the value of MNC that I want to determine. I want to find the line. Okay.
Yeah.
So I can minimize any of these functions. I don't care about the minimum, frankly. Okay. But to get to MNC, I have to minimize it. Both are related. Okay. All right. So I can use any of these functions. And why did I tell you all this? The reason for me, I mean, it's for me only and for you guys also, that when you read different books or different materials, none of them will tell you that all of these functions, if you do, or why they are using that particular function. They will say that let's minimize this. We will get MNC. Let's minimize this. We'll get MNC. None of the books will ever tell you that you can use any of these functions and you will get the same MNC. Okay. So when you read different books, don't get confused. Some of the books might be minimizing sum of squared errors. Some of them might be minimizing this ordinary least squares. Some of them will be minimizing mean squared error. But nobody will tell you what will happen if they remove 1/2 n. Nothing will change. Okay. You can minimize any of these functions. They will give you the same MNC. And all of them are convex by nature and differentiable. Okay. So which one do you want me to use? Because if I differentiate it, the constant will go to the other side. Okay. Which one do you want me to use?
Sum of absolute error.
Sum of absolute you cannot use. That's not differentiable.
It's squared errors.
Squared
Sum
errors.
of-
Okay.
Yeah.
So we are going to use the sum of squared errors. Okay. So you can use any function. There is no harm in it. And we want to, so yi hat is this m times x1i plus c. Okay, and we are doing to minimize it with MNC. So this, let's say this is my function j, which is a function of two variables m and c. Okay, I'm going to differentiate this function j, partially differentiated with respect to m, equated to 0, partially differentiated with respect to c, equated to 0. Can you tell me what will be the resultant equation? Will it be a linear equation or not? Think about it. Okay. Try to think of the like once you do the differentiation. So what is the current function? What can you comment about this current function? Is it quadratic?
Yes, it is.
Is it quadratic in terms of your MNC?
Mm,
Yes, right? Look at,
Yes.
I mean, you are subtracting yi minus mx1 plus c, and then you're doing the square of it. It's a quadratic function, right? If you
Yes.
expand it, it will come out to be a quadratic function in terms of MNC. So if you take the derivative of this function with respect to m, what will you get?
Linear.
A linear function. Okay. So this will be a linear equation. Yes or no? This will be a
Yes.
linear equation, right? In terms of MNC. Same thing. If you do the differentiation with respect to C, this will be a linear equation. Please note that when you are differentiating with respect to M, C will be treated as a constant. And similarly, when you're differentiating this with respect to C, M will be treated as a constant. Okay. Let's call this as equation 1 and equation 2. So if somebody gives you two linear equations, how do you solve it? I'll give you an example. Let's say these are two linear equations. Say 3x1 plus 4x2 is equal to say minus 3, and the next equation is 5x2 plus say 5x1 plus 7x2. Maybe say this is equal to 10. How do you solve it?
Elimination method.
Substitution, I think somebody mentioned, or elimination method. You can use any of the methods, right?
Matrix also.
Matrices also. You can use Cramer's rule. Okay.
Yeah.
There are many methods that you can use to solve it. Okay. Or the matrix based methods. Do you guys want me to show one of the methods, or you can do it on your own? Can you find the values of x1 and x2 which satisfy these two equations? Yes or no?
Yes.
You can, right? I mean, I don't have to explain it. Take x1, okay, write it in terms of x2, and you can say this is your x1. Substitute x1 in this equation, okay? So everything will be in terms of x2. This is called as a substitution method, okay? All right, at least you should know one method, okay? Elimination is nothing but you multiply them with a constant so that one of the term cancels out, okay? And then matrix-based solution requires Cramer's rule to solve it. Anyways, that's fine. We are only looking at these two equations. So my question is this: if I have two linear equations, would I be able to solve for MNC?
Yes.
Yes.
You can, right? So my variables in this case are x1 and x2. You will see two linear equations in the form of MNC. Now, one thing that I want to ask you is this: do you want me to solve this equation and get to the answer, or do you want me to directly tell you the answer and you look at the derivation at your own time? Solve it. Okay. I'll solve for one. See, I don't want to do it. Okay. It will take you guys extra classes. The more you want, the more you will suffer. Okay. Okay. I'll show you for one. Okay. Maybe I'll show you for one, and then you can go back and read about the other. Okay. What I'll do is I'll do it for this. Okay. Maybe I'll show you for how to do it for C. Okay. So I'm going to show you how to get this equation 2. Okay. How to get this equation 2. All right. You can do it for the rest on your own. It's a little complicated, so please follow this. I don't want to do this, frankly. Okay, but it's a little complicated. Okay. And you don't need to know the derivation. Trust me. Okay. So let's see how to do this, at least for one. This is your function. I'm just rewriting this carefully. I want to differentiate this function with respect to C. Once again, I want to differentiate this function, partially differentiate this function with respect to C, and then equate it to 0. Okay. Okay. How do we differentiate? The power 2 comes out. So 2 into the power will become what? 2 minus 1. And then you write the derivative of this inner term. Dx by dx. Okay, dx by dx. Does that, sorry, and this is dc in my case. Is this part clear? Yes or no? And this term will be equated to 0. The whole of this is going to be equated to 0. Is this part clear? Any questions?
No questions.
Okay, great. Okay, I'm going to write these individual equations. Please see to this carefully. So first find the derivative of yi with respect to c, then find the derivative of m times x1i with respect to c, and then you find the derivative of c with respect to c. You have to equate this to 0. I'm doing the derivative of individual terms. First for yi, then for this with a negative sign, and then for this with a negative sign. Okay. What will be the derivative of c with respect to c?
1.
0.
1. C is not a constant, it's a variable for us. Okay. What will be about this?
0.
0. M is a constant. X1i is the input value, again a constant. This would be a 0. What is this?
0.
0. Actual value. Okay. That is what you get. Okay. All right. So you are going to multiply everything with a -1 inside. Okay. Can I take this minus outside and say this is -2? Yes or no?
Yes.
Okay. And if
Yeah.
you equate it to 0, -2 can be taken to the other side.
0.
Okay. So that will go to 0. So this is what I have. And you will equate it to 0. Okay. So this summation, if you see, it is involved with this whole term. Okay. Summation is with the whole term. So what I'm going to do now is I'm going to write everything in terms of C. Okay. So let's look at this. So yi minus summation I equal to 1 to n m times x1i minus summation I equal to 1 to n C is equal to 0. Okay, I've taken C to the other side. If you add C n times, what do you get?
NC.
NC. Okay, so you get NC, right? I will take this n and divide this by n. So this would be a C. Can you tell me what this first term is?
Mean.
Mean of what?
Mean of the target values.
Target
Actual
values. Mean of the actual values. You can call it actual or target, whatever you want to call it. The y values. Okay.
Yeah.
And what is this term? See, m is a constant when you differentiated it with respect to c. So m can be taken out. You can write it like this. M can be taken out here. M is independent of I, right?
Mm.
M is independent of I. Okay. And what is this term?
Mean of the input features.
Mean of the input feature. One input feature. We have only one input feature. Yeah, this is the mean of input. Okay. So what is C? C is y bar, the mean of actual, minus m times x1 bar. Is this part clear? Look at this if you're not convinced. This is your y bar mean. This is your x1 bar, m times x1 bar. Is this clear?
Yes.
Okay. This is the mean of actual. This is the mean of x1. Okay. Now, to find C, can I do it without? Okay. Can I compute y bar and x1 bar from the data set?
Yes.
I can, right? But to find C, I also need m, right?
Yeah.
Okay. So if you do this derivative with respect to m, the same way you can do it. I'm just writing the whole thing, what you get at the end. It will again be like 10-15 minutes just to do this. I don't want to waste time. Okay. Derivation is not that important, trust me. Okay.
Okay.
M you will get is like this. Sorry. This is what you'll get. Okay. So do you think, is there any unknown in my equation? In this equation of M? Do I need to compute C for computing M?
No.
No.
So M can be computed directly, right? So first you compute M, then you substitute it here, and you will get C also.
Okay.
So this is the optimal solution for M and C. Okay, optimal solution for M and C. Clear? Is this clear?
Yeah.
Okay. Now, just a few things. This is the formula for your M. Look at the denominator. Can you tell me if it resembles something?
Deviation.
Is it it's something? Is it a deviation or variance? Something related to that. Okay. One thing I'll do is I'll add 1 by n on both sides, numerator and denominator. What does it resemble now? Denominator. Variance. And this term is called as, the numerator is called as actually the covariance. Okay.
Doesn't my x thing in the denominator cancel out with the x of the numerator?
No,
X,
this is in the summation. This is in the summation.
okay.
This is in the summation, okay? And both are the summations, okay? They are, so in the denominator, you are actually having sum of square entries. In the numerator, you are going to multiply x1i minus x1 bar into yi minus y bar. This would be for one sample. Then you will do it for the second sample, third sample, and so on. You cannot take x1i minus x1 bar common. It is independent on I. Okay, I get the point though. Okay. Now you need to know about one thing. So covariance is actually I would say covariance is nothing but computing the variance with itself. Okay, look at what variance is. Can I write this as 1 by n of summation of I equals to 1 to n, x1 I minus x1 bar and x1 I minus x1 bar twice? Yes or no?
Yes.
So can I say when I'm computing variance, I'm looking at how much is the deviation from the mean. I'm looking at with respect to myself and I'm squaring it up.
Yes.
Covariance is actually nothing but variance, but when you are computing for two different variables.
Yeah.
So one is x1 and one is y. Is that part clear?
Yes.
Yes.
Okay, there's a special name for it called as covariance. You're looking at how one variable varies with respect to the other. Variance is with respect to itself. Okay, variance is with respect to itself. Okay, so if you think about it, what we are doing is, see, I'm not sure whether you guys know what this term does. Are you aware if I subtract the mean from every entry, what will happen? We have discussed this, by the way. Okay, let's say I give you a feature. This is x1. Okay, let's say this is 1, 2, and 3. If I subtract the mean from, so mean is x1 bar. Okay, if I subtract the mean from every value, what will happen? You'll get 1 minus 3, sorry, 1 minus 2, 2 minus 2, and 3 minus 2. Can you tell me what happens to the resultant mean?
Minus 1.
What happens to the resultant mean?
Standardization 0. Mean would be 0.
Mean would be 0. I'm not standardizing it. I'm just ensuring that the mean becomes 0. So you are making the data zero centric. Do you know that when you are computing the variance, what you are doing is you are first ensuring that every point is zero centered, and then you are taking the multiplication with itself. x1i minus x1 bar, first it does the zero centering and then it computes the multiplication with itself. In covariance, you are centering all the variables up after you subtract the mean, so that resultant mean of your entire data is 0. Okay. So I'm not sure how much in detail your previous mentor went, but I'm telling you that's how variance is computed. You ensure that the data is around the 0. Okay. And then you are doing the multiplication depending on if you have like pairwise computations or you have computations with itself. Okay. Computations with itself is called as variance. Pairwise for different variables, it's called as covariance. Okay. All right. Okay. So we have seen one way of solving it, right? Okay. Now let's talk about multivariate data. Okay. Let's talk about multivariate data. See, there will be a lot of maths today. Let's finish this quickly. If you want to know more, see, you can get more out of me if you comply. Okay. All right. So now I have multiple features. So for one feature, how did you write the function? If you had one feature, how did you write a linear function? Y hat was
mx1 plus
plus c, right? I'm going to rewrite this just to make it generic. So I will write it like this: theta1 x1 plus theta naught. Okay. I'll just rewrite this just to show that, okay, m is theta1 and c is theta naught. Okay. If I have multiple features, I want to write a linear equation. How do I write it?
theta1 x1 plus theta2 x2.
Absolutely spot on. And so on till theta dxt plus theta naught. Okay. This would be your y hat. Is this part clear? Yes, people. Is this part clear? Now that you have multiple features, okay. So you will still minimize this equation. Yi minus yi hat. You'll still minimize this equation. So let me just mention this as, say, yi hat. So you will put I here, just to denote the index. Okay, just to denote the index. You can write it like this if that's what is bothering you. You can write like this. Okay, yi hat. You're squaring it up. You're minimizing this. Yi hat is this term. How many thetas do we have now?
theta1 to theta d.
A total of d plus 1 thetas. D plus 1 parameters. So for one feature, we have 2 parameters. For d features, we'll have d plus 1 parameters. Don't you think that you can repeat the same? So if this is the equation J, differentiated with respect to theta naught, differentiated with respect to theta 1, do it for up to theta d. How many equations will you have? How many linear equations will you have? D plus 1. How many variables do you have? T plus 1. Okay. Don't you think can be solved?
Yes.
Can be, right? So this is one way to do it. Okay. But I don't advise you to do this way. Okay. Because you'll be stuck if D is very large. Okay. Because you'll be solving these equations, right? And these equations will differ if the number of features are changing for different data sets. Okay. These functions will differ depending on what is the D. Okay. What is the number of dimensions? Okay. So I'm going to tell you now. Please mute yourself. There is this echo coming back. So what we are discussing right now is how to do this effectively for bigger data sets when you have more features. Okay. I don't suggest this approach. This can be doable. I mean, this is doable for sure. But this is infeasible in terms of the computations for data sets which are text-based, which are image-based, because those have around 30,000, 40,000 features and even more. Sometimes 1 lakh, 2 lakh features. So it is not practical to do it. You will not solve for 1 lakh equations. Storing the equations in the form of matrix and then solving them, okay, it is very compute intensive. So I'm going to show you something like this. So what I'm going to discuss now is a solution. Okay, I'll directly tell you the solution. If you're interested, maybe we can discuss about it in free time at the end of the course, not right now. Okay. So I'm no instructor will tell you this. You can watch recording from any other instructor. I can promise you that. Okay. So what you need to know is the following. When you want to solve these equations, right? Okay. When you want to solve this, especially when the number of features are large. Okay. Okay, where yi hat is this. What you can do is you can write this equation as in terms of matrices. You can actually write this equation in terms of matrices and vectors. In terms of matrices and vectors, and then you can differentiate this equation with respect to vector of thetas. With respect to vector of thetas. This is called as matrix differentials. Okay, I didn't ask you to study this because it will require some rules which you would not have studied before. It's usually taught in undergraduation courses in probably the second year and third semester. So it depends on like from which institute you are doing. So I cannot say if any like everyone covers it, but it is typically taught by. It is called as matrix differentials. Okay, so you differentiate matrices now in terms of vectors. So you can write everything in terms of matrices and differentiate it with respect to vectors. I can show you the derivation. There is no point in understanding the derivation right now. Okay, even in your interviews, nobody is going to ask you the derivation for it. But what you need to remember is this. So if X is the data set that you have, this is the data set that you have with D features. Okay, assume that you have n rows. What would be the size of it? If you have n samples, what is the size of it? N cross D, right? Okay, N cross D. Okay, I've written the symbol R to denote that there are numbers in it, real numbers in it. Okay, if you look at the output, what would be the size of it?
N cross 1.
N cross 1. Okay, so this output is say N cross 1. Okay, I'll just make them as capital and small. Sorry, this is N cross 1. Okay, what you need to do is you need to do one change. You have to add one more column here. This is X naught, and this X naught is always 1. Okay, so what is the size of this now?
N cross D plus 1.
N plus D, N plus 1. Oh, sorry, N comma D plus 1. You're right. N comma D plus 1. Okay. This matrix is called as X. Okay. This column vector is called as Y. Okay. The thetas that you have. Please, can you mute yourself? There is an echo coming in. So the thetas that you have, there are D plus 1 thetas. So this would be D plus 1 times 1. Okay. You can directly get these thetas with the help of this formula. This solution is called as normal equations. It can work for univariate, multivariate, anything. Okay, if it can work for multivariate, it can work for univariate also. Okay, it's called as the analytical solution, also called as the closed form solution. Many books refer to it by different name. Okay. Now I want you to focus on this solution. Okay, X is this matrix. Okay, which is this N times D plus 1. You just appended a column X naught to it. Okay, Y is this N comma 1, and theta is this D plus 1 comma 1. Okay, my question is this: which so T stands for transpose. This means transpose of a matrix. So if I give you A comma B matrix, what would be the transpose of it? B comma A, right? You will make rows as columns and columns as rows. This is the inverse. I hope you know how to compute the inverse. Okay, you make use of the adjoints and the cofactors and divide by the determinant. Okay, if you do not remember, please go back. This is again a 8th or 9th level thing. Okay, so maybe do it for a 2,2 matrix and a 3,3 matrix, and you'll be able to revise. It will take you 10 minutes max. Okay, so revise how to figure out the inverse of a matrix and how to do the transpose. Okay, my question is this: what would be the size of this extra? Okay, for what matrices you can take the inverse? Square matrices only. Only for square matrix you can take the inverse. The matrices of the form of A comma A, A cross A, B cross B, and so on. The number of rows and number of columns have to be the same for you to take the inverse. Okay, what is the dimension of X transpose X? What is the dimension of this?
D plus 1, comma n.
Comma D plus, no, the whole thing. Okay, so X transpose would be this. If you multiply with n comma D plus 1, what do you get?
D plus 1 comma D plus 1.
D plus 1. You can see that it's a square matrix, right? And you are taking the inverse of it. Okay. So if inverse is actually a very expensive operation. Okay, I'm just letting you know, inverse is an expensive operation. So I don't know, like if you know about the inverse or not. So if you have a D cross D matrix, D plus 1 into D plus 1 is again of the order of D comma D. Okay, D cross D. So if you have a D cross D matrix, it takes around D cube operations to get the inverse. Okay, the fastest method that I know of, it almost takes around D to the power of 2.71 operations. Almost. Think about what will happen if D is large, if the number of features are high. Do you think this method is practical? Okay, let me ask you this. If D is 30,000, what would be the size of X transpose X? 30,001 into 30,001. Have you ever seen such a big matrix being stored?
No.
No, right? I mean, I hope you get the point. Okay. So first, computing X transpose X is a big deal. It has a lot of additions and multiplications. Another is when you want to take the inverse, it is even more expensive. Okay. So, I mean, when number of features are large, this method kind of becomes impractical. Okay. When number of features are large, I mean, you do not have enough memory in your computer to solve it. Okay. You become devoid of your RAM, computer RAM, because computer RAM is limited in terms. I mean, if you compare it with your hard disk, right? Your computer RAM is just 8 gigabytes, maybe 16 gigabytes, maybe 32, 64, maybe 128, maybe 256 if you are in a cluster. It is not more than that. Maybe if you are working for the biggest company, say Facebook, Amazon, they will not even give you a RAM which is greater than 512 gigabytes, no more than that. Okay. If you think about this matrix 30,000, 30,000, it will actually be of the same size, 512 gigabytes. Now you can solve it. Okay. But nobody is going to give you access to that. Okay. So you cannot solve for such big matrices. This is infeasible. Okay. Taking inverse is infeasible. Okay. So I'm going to show you one more way of solving it. And so you can solve it for small data sets. Okay, for smaller data sets, this is okay. Okay, for smaller data sets, even if the number of samples are large, this is okay. Okay, when D is small. Even when N is large, you can do it. Okay? Even when N is large, you can do it. However, when D is large, you cannot. Okay, so this is okay for smaller data sets, not okay for bigger data sets when number of D is large. Okay. Okay. So let's see what is the third method that people use. Okay, what is the third method that people use? And this method would need some patience from your side. Okay. Okay. So I'll take it from a generic example, and I hope that you'll be able to generalize that example onto the equation that we have. Okay, onto the equation that we have. So we have this equation, right? Summation I equals to 1 to n yi minus yi hat whole square. Okay. Where this is this. All right. So we are trying to minimize this. I'm putting just a 1/2 outside because it will make my equations simpler. Thetas will not change. Okay, thetas will not change. Okay. All right. Let's see how to minimize this equation. Or rather, let me demonstrate with a small example how you can minimize it with the third way of doing it. Okay. So the method that we are discussing is called as gradient descent. Okay, let's see how it works. Imagine I'll take this function, say 3x square plus 6. Okay. All right. So find me that value of x. Okay, find me that value of x which minimizes fx. Find x which minimizes fx, which gives the least fx. This is what we have to solve. What is that value? What is that value of x which gives you the least value of fx? This is your fx, by the way.
6. Oh,
So x is what?
0.
0. So we are interested in finding this x is equal to 0, which gives me this minimum. So I want to reach to this location. Okay. Forget about what you have studied so far, taking the differential and equating it to 0. You will do similar things though here. Okay, let's talk about this. Okay, so first let me give you an intuition about what is a derivative. Okay, you need some more intuition about this. So given a function, okay, given a function, let's say this is the function, right? And I am computing the derivative of this function, maybe say at the value x is equal to 5. Okay, so whatever that function is, this is the value of function at f of 5. Okay, the derivative implies that derivative is nothing but the slope. Okay, the tangent at this point, okay, 5. Okay, the tangent at this point to this f of 5. Okay, can you tell me what would happen if you are at one of the points, which are the minimas or the maximas?
horizontal.
So it will be exactly horizontal. So what is the angle? So at the minimum, if you look at the minimum, what can you say about the slope?
0. Theta is 0. Right? Angle is 0.
Theta is 0, right? So what would be m? Slope, what would be the derivative at that point?
1.
Again, think. Tan of 0 is what?
And 0 value is 0.
0. Sin theta by cos theta. Sin 0 is 0, cos 0 is 1. Okay, so 0 by 1 is 0. Does that make sense?
Yeah.
Okay, see, we say that this is m is nothing but differential, which is the derivative, the slope. Okay, slope is given by tan theta. So do you realize that when we are trying to get the derivatives, how do we get the derivatives? We do the differential as equal to 0, right? Yes or no?
Yes.
Yes.
That is why we do it. Okay. Do you realize that now?
Yeah.
That is why we do it. Because the slope is 0 at that point. Even if you look at the maximum, the slope is 0. Okay. All right. So derivative is the tangent at that point. Okay.
In other terms, we can say slope is the rate of change of y with respect to x. Now the y is
Spot on.
same.
Spot on. Yeah, the y is same at the minimums. Okay. Y is same at the minimums and the maximums. The rate of change of your function is the same as at the minimum and the maximums. Okay. Spot on. Okay. All right. Okay. Now let's try to understand this concept. Okay. So before I discuss this concept, we still have 13 minutes. I'll be able to discuss this concept in somewhat detail. Imagine that I have given you a wire. Okay, this surface of this function is like a wire. Okay, and now you want to find the minimum of this wire. Okay, now you want to find the minimum of this wire. Can you tell me, if you were a kid, how would you find the minimum of this wire? I can tell you, your child, if you have a kid, okay, your kid can do it. You can use any prop. You can use any object that you want.
With the ring, we can.
You can use anything.
Ring.
So with the ring, what would you do?
I put it in.
No, I mean, if it's a ring, I mean, if it becomes horizontal at a certain point, it is not going to work. It may not work. Think of maybe a circular object, a sphere, maybe a ball. That should give you a hint. Ring will also work. I mean, if you're thinking in 2D, ring, if you're thinking in 3D, it may not. Okay. Okay. So what would you do? So let's say if you roll a ring down this surface, where would the ring settle? Where do you think the ring settles? So let's say I have a ball. I start rolling this ball. I mean, I don't even roll this ball. I just leave this ball as it is. Okay. Where do you think this ball will settle? Don't you think this ball will go down?
Yeah.
Where there is no slope.
Well, there is no slope. That's the point of it. At the minimum, it settles, right? Yes or no? Okay. I mean, it might go up, and then it will come back. Yes or no? If it has extra momentum, it will go up and then it will come back. But it will settle at the minimum, right? Are you convinced or not?
Yes.
Yes.
Okay. And what can you say about, okay, what can you say about, so if I look at, okay, let's say we are at this value 5. So what is the function value at 5? 81. Can you compute the function value at 5? This is 81, right? Yes or no?
Yes.
Okay.
Yes.
This is the function value at 5. Can you tell me what is the gradient of this function at 5?
Slope, right? So
Slope is 6x
30.
30. So gradient is 30. Okay, I want you to focus on this. What is the gradient at this minimum?
6.
0. At x is equal to 0, what is the gradient? 6 into 0, 0.
Yeah.
Minimum is 6. Okay, minimum is 6. Fx is 6, but the gradient is 0. Okay, I need you to realize that if you go above, I mean, if you choose any other value of x which is beyond 5, the gradient increases. Yes or no?
Yes.
Okay. I mean, as x increases, 6x also increases, right? Okay. And if you're on the negative side, what happens? Okay. Yeah. Gradient decreases or increases? If you're on the negative side. If you go towards the negative side, what happens to the gradient? Let's say you are at -3. What is the gradient right now? Minus
Minus
18.
14.
If you're at -5, what is the gradient?
Minus 30.
Is it more or less?
30 is less than
Less,
minus.
right? It's less. So if you're on the negative side, your gradient is decreasing. If you're on the positive side, your gradient is increasing. You need to realize just one thing. If you are moving, see, let's say you start at 5. Do you realize that if I want to reach to the minimum, I need to move in the opposite direction of the gradient? Yes or no?
Yes.
Okay. If I go to the right hand side, what will happen? I'm moving in the direction of the gradient, right? Where the gradient is increasing. What is the gradient at this point? 60. So if I go in the direction of the gradient, where the rate of change is more, I'm moving away from the minimum. Okay. Now think of this. If I'm at -3, okay, if I'm at -3 here, if the ball is here, okay, what is the gradient right now? -18. Okay. If I move to the in the opposite direction of the gradient, where let's say I'm moving in the direction of the gradient. Okay, let's say I'm moving in the direction of the gradient, where gradient is actually now decreasing. Okay, where gradient is actually now decreasing. Am I moving in the correct direction? Am I moving in the correct direction? If I move where the gradient is decreasing?
No.
No. Okay, but if I move in the opposite direction of your gradient, what happens? I move to the correct side, right? Okay. So one thing that you need to realize is you can reach to the minimum. Okay, I'll just highlight this fact. You can start from anywhere. Okay, you can start from anywhere. I'll show you with examples also. You can start from anywhere. Okay. You have to move in the opposite direction of the gradient. In the opposite direction of the gradient to reach to the minimum. Okay, opposite direction of the gradient to reach to the minimum. Okay, to reach the minimum. See, you can only use this method if the function is differentiable, because we are differentiating it. Okay, finding the gradient needs differentiability. Okay, let's see with a small example. Okay, so I am saying that, so there is some start point. Okay, let's call it as x start. Okay, let me write it like this. Okay, this x start is the point where I'm at initial point. Okay, I'm going to subtract the gradient from it. How do we write the gradient? We write it like this, right? The derivative of this. Okay, and what is the gradient at x is equal to start? So at x start. Okay, wherever I was at, I want you to focus on this, and this becomes my x, say, updated. Can you tell me if I moved in the correct direction or not? Where do you want to start? Tell me. Where do you want to start? Let's say this is the function, 3x squared plus 6. Give me some value of x where you want to start.
X equal to 5.
Okay, let's say I want to start at x is equal to 5. Okay, I am here. Okay, I am at this point. I am at this point. Okay, my function value is what? 81. Okay, my function value is 81. What is the gradient at this point?
30.
So gradient is 6x. And if you put x is equal to 5, you get gradient as 30. Okay, let's go a step back and try to do this. Okay, so if you look at your x start, what is x start? 5. Okay, you are going to subtract the gradient from it. So this is your gradient at x is equal to 5. What is the gradient?
30.
30. Where do you end up?
Minus 25.
Did you move in the correct direction or not? Look at this. You were here, you jumped to minus 25, but did you move in the correct direction or not? Yes or no?
The opposite direction.
So we have moved in the opposite direction of the gradient, but did we move in the correct direction or not? That's the question. Did we move towards the minimum or not?
Yes. Yes.
We did, right? Keep this in mind. That's the only focus right now. Okay. Let's say you were on the negative side. Okay. Let's say you were at, say, minus 10. Okay. So what is the gradient at minus 10? Can somebody tell me?
Minus 60.
Minus 60.
Okay. Look at this. Minus 10 plus 60. This will be 50. Do you realize that you'll move to plus 50? Did you move in the correct direction?
Yes.
Okay. So if you move in the opposite direction of the gradient, you move right. Okay, you move towards the minimum. That is one thing. Now, the important aspect is this. Do you realize that there is a problem if I'm doing this? And what is the problem? Can you comment on it? Don't you think you're over jumping? You're kind of overshooting the minimum. Yes or no? So, do you think I can control this jump by multiplying a factor? Let's say I'm controlling this jump by multiplying a factor. I'll represent it like this. Okay, eta. Eta is called as a learning rate. Okay, this learning rate is typically given in the forms of 10 to the power minus k, where k is any number, say 1, 2, 3, and so on. Okay. So basically 0.1, 0.01, 0.001, and so on. Okay. So I'm going to take a number. Let's say eta is 0.1. Okay. I'm going to take this number. So if this number is more, what do you think happens? Do I take a bigger jump or do I take a smaller jump?
Bigger jump.
Bigger jump, right? Okay. So if I use eta to be 0.1, this is called as eta, by the way, the learning rate. Okay. Also called as eta. Okay. The symbol is called as eta. So where do I move? 5 minus 0.1 into 30. So where do I move exactly? 2. Okay. Do you see that from 5 I actually move to 2? Okay. From 5 I move to 2. What is the function value at 2? Put x is equal to 2 in the equation. 3x squared plus 6.
18.
18. Okay. Do you realize that I moved in the correct direction? Okay. I am reaching towards the minimum. Can you repeat this process for 2? So you are at 2 right now. What is the gradient? 6x. If you substitute, so eta is 0.1. You're going to multiply this with the gradient. Gradient is 6x. At x is equal to 2, what is the gradient? 12. Yes or no?
Yes.
Yes.
Okay, so 2 minus 0.1 into 12. This would be 2 minus 1.2, 0.8. Does this make sense? So you're coming from 2 to 0.8.
How
Is
do
this
I
what-
decide the value of k?
How do I decide?
The value of
That is
k.
what I'll come at that. Okay, I'll come to that. I've just chosen currently k to be 1. Okay, but is this so far clear? Okay, can you repeat it for one more time for 0.8? I just want to show you that you will reach to a value closer to the minimum very, very soon. So 0.8 and you subtract this 0.1 into gradient is 6x, that will be 4.8. So this will become 0.8 minus 0.48. So this is 0.32. Okay. Hope my calculations are correct. So you are here. Do you realize that if I keep on doing this, I will reach to the minimum? Yes or no?
Yes.
Okay. But what is happening at every step? Is my step size reducing or increasing?
Reducing.
Reducing, right? This is the step that you take. So this component that you see is also called as the step size. The jump that you are taking. Okay. So if eta is big, can I say eta regulates the jump?
Yes.
Okay. The learning rate regulates the step size. It controls how much the jump is. Okay. Let's say if I say eta is say 0.5. Just imagine eta is 0.5. What will happen? Will you overshoot or will you, will you be okay? If you were at 5, eta is 0.5, where will you end up? So you are at 5, eta is 0.5, and the gradient was 30. So this is 5 minus 15, which is minus 10. You overjumped, right? Yes or no? So what can you say about it? Okay, if you were at minus 10, can you tell me where will you end up?
Minus 2.
At 20. Do you realize that if you repeat this process, if your eta is too large, you will never converge. It will just keep on increasing. It will be like this. Does this make sense?
Yes.
If eta is too large, you will never converge. So eta has to be small. Okay, keep that in mind. Okay, I'll just remove some of the things which I described here. Okay, I'll make note of it on a separate slide. Okay, so regulating eta is important. Okay, that is one thing. Okay, regulating eta is important. I need just 3 more minutes, please. Okay, so if eta is big, what happens?
Overjump.
You basically diverge. You do not converge to the minimum. Okay, if eta is big, you'll be diverging. It will happen like this. If you start from here, it will go here, then it will go here. You will never reach to the minimum. Okay, and if eta is small, what will happen?
Step size will be very less.
Size will be very less. So you'll be moving like chunks like this. It will take you a lot of time to reach to the minimum. Okay, too much time consuming. The number of steps that you require to reach would be a lot. Okay, so we have to regulate this eta. Okay, you have to regulate this eta. I'm going to talk about how to regulate this eta tomorrow. For now, you just need to remember this. So given a parameter, let's say I have a parameter. Let's call this parameter as x, or rather I'll call this parameter as theta j. Okay, so I'm going to write it like this. So theta j of m equal to, so this is like the current value. Okay, this is like the current value. You are subtracting the eta times, given a function, you're going to compute the gradient of this at theta j of m, okay, and this value will give you the next value. Does that make sense? Yes or no? Is this part clear?
Yes.
I've just written it like this, okay? So, how many thetas are available for a d-dimensional data set?
+1.
D plus 1. So,
D+1.
j values can take from what to what? 0, 1, 2 up to d. Does that make sense? See, I have to, so it is like this. I have d plus 1 thetas, start from any value of d plus 1 thetas. You can take any value from d plus 1 thetas, start everything by say 0, put everything as 1. It is up to you. Okay. Put equation as, put the values of all the thetas as anything. And now you update all of them. Okay. And you keep on updating till when? Till when you reach the minima. Okay. You reach the minima. Okay. This is called as gradient descent. You use the gradient. You use the opposite direction of the gradient to descend into the minima. Okay. Using the opposite direction of the gradient to descend into the minima. Okay. Gradient to descend into the minima. Okay. We'll discuss more about it, how it is, I mean, much, you can say, less compute intensive. How do we optimize this eta? Okay. How do we find a good value for it? We will discuss about it tomorrow. Okay. So this is it from my side today. Any questions? And this equation is called as, just a second, I'll just write this. This is called as the gradient weight update equation. It's simply called as the weight update equation because parameters, they are also called as weights. Okay, parameters, coefficients. Okay, you can also call it the weight update rule. Okay, or weight update method, whatever you want to call it. Okay, it's also called as gradient weight update. Okay, I'll stop here. Any questions? Please ask.
So Sanatan, I have a question not related to today's session.
Mhm.
Like when we train any model, then the data which we used yesterday as an example from the scikit-learn library,
Mhm.
that the data was already encoded, but the real data set that we,
Yes,
Okay.
you have to encode them.
so first step would be encoding and then doing
Correct.
all the scaling and everything.
Correct. So first step is typically pre-processing. And I believe many of the mentors have taught you how to pre-process the data before.
Yeah, we have gone through that knowledge, but we went through like this min-max scaler and standardization also. But how and at what point of time we use it in the machine learning, we are like.
I hope now it's clear at least. At what
Now
point
it's
you'd use
clear.
min-max scaler?
So can we also inculcate the first step, that is the encoding step also in the next?
I can do that. Okay. There is, but again, if I do it every time for an algorithm, don't you think it will be time consuming?
No, only just once, like you did
All right.
normalization.
You okay? What I'll suggest you is bring me a data set where you want me to show how to encode. I've already shown you individual encoding steps. So my suggestion is like bring me a data set that you want me to work on. Please keep it as a regression data set for now, since we are working with regression. Others will not understand it otherwise. Okay.
Okay.
Bring me any data set where you want me to show explicit encoding schemes. I'll put those and we'll take it up from there. Will that be okay?
Okay, I'll search for that data set.
Anything is okay. I will show you on a subset of it. Okay. Because I want to save time. I cannot keep it running in this 2 hours class. Okay.
It's just once that we are clear with the steps from the scratch, how we start.
That I will do at the end also. I'll try to show you on this entire, using all the algorithms. Okay. I'll show you, see this, what we are doing is, this is just the beginning. I will actually show you libraries where you can train 30 to 40 models in one shot.
Okay.
Okay. So we will reach that. We will reach there slowly. But if you want me to show some of the basic pre-processing steps on a data set, bring one to me, I'll show you.
Okay.
Okay. All right. The reason I don't do that because I want to save time. We already have pre-processed data sets. Okay, I prefer using those. Why would I waste my time every time when I'm looking for one explicit data set? Because
Yes.
the data only differs, right? Algorithms, they don't.
Correct.
Okay. Yes. So you can bring me one. I'll show you in the next class how to do it.
Okay.
And anything else about the topics that we have studied or anything? So we'll be discussing why this approach is not compute intensive. We'll discuss that in detail. Okay. We will also see how to control this learning rate. Okay. We will also see like different variants of gradient descent, which are even less expensive. Okay. And we will see the impact of this gradient also. There are a few things that we have to discuss. Okay. And with this, linear regression would finish. And then I'll show you how to do polynomial regression, like quadratic, cubic, and so on of any power. Okay. So tomorrow, half of the class would be about those, about the theory, and the latter half would be about implementation. Yes.
So all those topics, theoretical topics that we have covered today related to linear regression, like I know there would not be a single link having all these things, but could you just suggest some of the resources that we can go
I'll put
through?
a resource.
Okay.
I'll share some slides where all the derivations are there. I'll also share some notes where there will be advanced details. If you want to explore those, I'll also put up a book if you are keen on referring to. Okay.
Okay.
I'll do that. Anything else I can help with? But I'll do it. So I have another meeting at 11:30. I'll upload everything. I mean, these notes today and maybe some slides. But the book and other things I'll upload maybe, say, in the next 2 hours or so. Okay, in the next 2 hours or so. Okay, handwritten notes I'll upload it right away. Okay, and the some slides for you to look at the derivations. I'll do that. Okay, but wait for the book, and I mean, you can actually check it after 2 hours if you want the book. All right. Okay, anything else I can help with? Tell me. Any questions from anyone? You can write to any account now. Okay, if there are no questions, then we'll meet tomorrow and we'll discuss all these things. Before you come for the next class, please revise if you can. Okay, if you have some time, maybe spend 20 minutes. Okay, at least look at what we have discussed so that you have a fresh understanding of what we are going to cover tomorrow. Okay, all right, bye everyone, take care.
Thank you.
Yes. Any other things? You can ask. Okay, I'll wait for 5 minutes. That's okay.
No, sir, thank you.
All right, take care, guys. Bye-bye.